Hi, today we are going to learn a very interesting algorithm called merge sort. And this merge sort algorithm runs on a paradigm called divide and conquer. So, what is divide and conquer? If we can break a single problem into smaller subproblems and then solve the smaller subproblems, combine their solutions to find the solutions for the original big problem, it becomes easier to solve the whole problem. Let's go back to the history where these divide and conquer came. So, as an example, I can say that I was born in Indian subcontinent, and once upon a time, the British conquered the whole India. So when British went to India, they saw a country with different religions living in harmony. So the people was hardworking, but they were naive. So there were unity in diversity. And the British found it difficult to establish the empire. So they adopted the policy to divide and rule. Like the population of India was collectively a one big problem for them. They divided the problem into smaller problems. How? By instigating rivalries between local kings, making them stand against each other. And this worked very well. Well, that was history and a socio-political policy, which is called divide and rule. But the idea here is if we can somehow divide a problem into smaller subproblems, it becomes easier to eventually solve the whole problem. So you can see that in the divide and conquer actually works on three principles. First of all, divide the problem into multiple small problems. Second, conquer the subproblems by solving them. The idea is to break down the problem into atomic subproblems where they are actually solved, and then combine the solutions of the subproblems to find the solution of the actual problem. In this figure, you can see that this original problem is divided into two subproblems, and then this subproblem is conquered by calculating or whatever you do. You find the solution of this subproblem and then combine this solution. So, and this final solution actually the solution to this original problem. Now, in computer science or in our computer machine, this algorithm of dividing the original problem into subproblem actually works recursively. How? I think you already know how recursion works. So if it is the original problem, we will look if it can be subdivided into subproblems. Suppose we can divide it into two subproblems. Okay, then go to the left. It's like the divide of the original problem to the subproblem is top to bottom approach. Okay, we go to the left subproblem first and then see if this subproblem can be divided into additional subproblems. Okay, suppose we can divide it into additional two subproblems. And at the bottom, we will check if that subproblem can be divided into additional subproblems or not. Suppose this is an like atomic problem and you cannot divide it into additional subproblems. Then we stop here, we go back, and we already know that we have another subproblem to this subproblem. We solve this problem, we merge these two solutions, go back, and then we already know that we have another subproblem to solve. So we go to that subproblem and divide this subproblem into additional subproblems. This is an atomic subproblem. So we solve that, and we have another subproblem to solve. We combine the solution, get the solution to the subproblem, and then finally we combine the solution to this subproblem and this one. Then we got a solution, and this solution is actually the solution to the original problem. Okay, let's get into our merge sort algorithm. As we have already discussed that merge sort utilizes divide and conquer rule to break the problem into subproblems. The problem in this case, since it is called merge sort algorithm, the problem in this case is sorting a given array. So in merge sort, we break the given array midway. For example, like we have an array of length 4. That means the index will be 0, 1, 2 to 3. So if we want to divide that problem, then we will have to divide it in the midway. So the merge sort will break it down into two subarrays with 2 elements each. One is 0, 1, and another subproblem is, or another subarray is 2 and 3 index. Okay. Now, now let's see the merge sort algorithm. Here, you can see that our merge sort algorithm should be provided 3 parameters. One is the original array, and another one is the left index, in this case, which is 0, and the right index, in this case, which is 3. And then we'll check if left index is less than right index. If our left index is less than right index, then we calculate the midway, which is left plus right divided by 2. So we are dividing the original problem into 2 subproblems in the midway, which is Q. So we used floor function here. You will see why. So after getting the midway, we call the merge sort function recursively, and one of them is with the original array, the left index, and the middle index. And then the merge sort with the array and the mid plus 1 to right index. That means we are passing the left subproblem, which is left subarray, and the right subproblem, which is right subarray. And then we call merge function. Okay, so in this picture, you can see that our original array length is 0 to 3, which is length is 4. So if we divide it, then you will get 2 subarrays, which is 0 to 1, and another one is 2 to 3. And then we go here, and if we subdivide it, we can see that there are actually 2 elements in the subarray. So we divide it with the A0, which is one subproblem, and A1, which is another subproblem. So, and if we go to this subarray, we'll see that this is also like, it also have 2 elements. So we can divide it with 2 subproblems. One of them will have array with one element, which is index 2, and then array index 3. Okay, now we know how to divide the original problem into subproblems. So if we see in this picture, we see that there is an array of length 1, 2, 3, 4, 5, 6, 7, length of 7. So we already know that we have to find the middle way, which is left index plus right index divided by 2, which is 0 plus 6 divided by 2, which is 3, 1, 2, 3, 4, 5, 6. Now let's see another example on a different array. So you can see that this array is length of 1, 2, 3, 4, 5, 6, 7. So it is the length of the array is 7. And then we divide the array into two subarrays. This is the left subarray and the right subarray. And on the left subarray, we can see that this can be divided into further subarrays. So we divide into two subarrays, which has left one has two elements, 38 and 27, and the right one has two elements, 43 and 3. And then we go to the left subarray and let's see if we can subdivide. Yes, we can subdivide it because the length is 2 and we can subdivide it with one of them will 38 and another subarray will be 27. The rest of the arrays are divided in the same manner, in recursive way. So after that, we can see that at the last step here, we have the atomic subarrays. That means we cannot divide this array into additional subarrays because they have only one element. Now we start combining the solutions. Actually, this atomic subarray is actually already solved. You don't have to solve this or you don't have to sort this array because it has only one element, 38. You cannot sort it. Okay, the solution to this array is 38 and the solution to this array is 27. So if we merge the solution, we will look for which one is smallest. Okay, 27. Okay, in our merged array, we will store it as 27 and 38. Same here, among 43 and 3, 3 is smaller. So the combined area will be 3 and 43. And here, the smaller is 9, between 9 and 82. So the combined area will be 9, 82. And this one is 10. And you don't have any additional subarray to look into. So the solution will be 10. It will be carried out to the next steps. And in this step, we will see that among 27 and 3, 3 is less. So see 3 is lesser than 27. So we will take 3 first, and then we'll look for 27 and 43, who is smaller, 27, then store 27 first, and then we move to 38. And among, like, in this 38, when we're taking 38, we don't see, okay, we already took 3. We have only 43 to compare. So 38 is less than 43. So we'll take 38. And then we have only 43 left. So add that 43. In this way, this merge comparison and merging the solution will happen. So we know how to divide the original problem into subproblems, how to merge. But now let's look into the merge function in detail because we see some complexity here, like while merging, how to compare the elements and how to take the remaining elements to the merged array. Okay, let's look into our merge function. Merge function actually merges two subarrays and sort them and store them in a combined array. So here in this picture, you can see that we are tracking the index of subarray 1 and subarray 2 by variable I and j, which are initially 0. And then the combined array with the variable k. So k will be initially incremented. That means k will be 1. Let's start comparing and combining the two solutions. So we will compare the first index of subarray 1 and with the first index of subarray 2. So we can see that the elements are 1 and 6. And if we compare, who is smaller, 1 or 6? 6, right? Okay, I'm just kidding. 1 is smaller. I'm taking this 1 into combined subarray. Okay, I'm storing the result. This is one of the result, 1. And then we'll go to the second index of subarray 1, which is 5, and the first index of subarray 6, which is 6 in subarray 2. So if we compare 5 and 6, then we'll see that 5 is smaller. We'll take 5, we'll increment the value of k, and then we will go to the third index, which is 10. And in the first index of the subarray 2, which is 6, who is smaller? 10, right? That is why I took 10. Okay, I did it intentionally so that you can catch the problem. Here, which one is the solution, 6 or 10? 6 will be the solution. So you will have to store 6 here, not 10. Okay, you can find the solution here, 1, 5, and 6. Okay, when we are at 10, we'll see that among 10 and 9, the solution is 9 because 9 is smaller than 10. We will actually store 9 here, not 12. Okay? Okay, the solution is here, 1, 5, 6, and 9. There's a problem here. The problem is we are at the second index of subarray 2, but we are not finished with the subarray 1 yet. What will happen? Who will be comparing with which one? Like which element of subarray 1 will be compared with subarray 2, since we are done with subarray 2. So that is a problem here. How to solve that problem? Okay, let's see what happens. Okay. Since we are at 10 and the subarray 2 is already finished with the processing, then what we will do is we will take all the elements, like remaining elements of subarray 1 to the combined array. That means we'll have to copy this 10. Okay, I'm copying this 10 and copy this 12, which is 12. Okay, what about, like, if we see that we are finished with processing subarray 1, but we have remaining elements in subarray 2, what we will do? Do you have any idea? Okay, I'm telling you. So if we are finished with subarray 1, but we have remaining elements in subarray 2, then what we will do is we will take all the elements, like the remaining elements from subarray 2 to the combined array. That is why you can see that the code here is, if, like when we run out of elements in either left array or right array, we will just copy those elements into our, we'll just copy those elements into our combined array. That is how we write the merge function. Okay. Okay. So now we already know our merge function and we already know how merge sort works. So if we combine those two solutions, then we will have our merge sort. The merge sort is quite fast and has a time complexity of big O of n log n. You guys have idea about what is big O and what is complexity of an algorithm, right? So in this section, we will understand why running time for merge sort is n log n. Why? So as we have already learned in some other algorithms like binary search, that whenever we divide a number into half in every step or an array into half of array in every step, then it represents a logarithmic function, which is log n. And the number of steps can be represented by log n. Also, we perform a single step operation to find out the middle of an subarray. Do you remember? So here you can see that we are calculating this Q in every step. So it will take a constant time, which is big O of 1. Okay. And to merge the subarrays made by dividing the original array of n elements, so a running time of big O of n will be required, right? We are merging all the subarrays. So in total, the length is n. That means we are doing n work. That is why running time of that part is big O of n. Hence, the total time for merge sort function will become n log n plus 1 constant time to find the midway, which gives us the time complexity of big O of n log n. Okay, in case of this merge sort, worst case, best case, and average case, all the complexity are n log n. Why? Because even if the array, the main array is sorted, you will have to subdivide the arrays until you find the atomic array, and then we'll have to compare. No matter if it is sorted or not, if it is best case, worst case, or average case, you'll do the same work. That is why in every cases, the complexity of merge sort algorithm is n log n. And you know that what is space complexity? And you already saw that it requires equal amount of additional space as the unsorted array, because you have to create the subarrays and then compare them and combine into one solution. So the subarray you are creating, they are taking space. So, and how many or how much space? It is equal to the number of elements you have in your original array. That is why your space complexity is n. Okay, that's all for our merge sort algorithm. Do you have any questions?